Okay, I think we'll get started. Welcome to the second of our labs on machine learning for general chemistry, part 1. And today we're going to be predicting properties of fake materials, and we'll see how we will use several different machine learning models to accomplish that, and we'll be able to compare and contrast the different models for this particular situation. So, we're going to be working with a large data set, 50,000 samples, and the relationship between those properties are given in a large, just comma-separated values data sheet. The type of learning we're doing here is under the category of supervised learning. So we will give the machine learning algorithm the two properties and the third property in this test, in the training set, and then it will be able to learn by comparing against the right answer. So in supervised learning, there's always that right answer that it gets to compare against. And we'll look at the analysis of these models using some of the ideas we talked about in the last lab. So actual versus, or predicted versus actual plots, residual plots, and the mean absolute error and the mean standard error, and then the R-squared. Okay, so we're going to contrive a very simple scenario, and we're going to imagine this alternate universe called Cobberland. Now, the name comes from Concordia College, where I teach physical chemistry. Our mascot is kind of a strange mascot. It's called a cobber, and it is a fierce-looking cob of corn. So a lot of the things on our campus have corn puns in their names, and so we'll just follow that here in this new world called Cobberland. And the scientists in Cobberland are called cobbers, and they have studied matter, and all matter is made up of things called kernels. Kernels have only 3 properties: irritability, amazingness, and stockiness. Irritability and amazingness are easy to measure properties of the kernel, and stockiness is a hard to measure property for these cobber scientists. To date, the cobbers have developed 50,000 known kernels, completely characterizing the irritability, the amazingness, and the stockiness. And we're going to try to find when we find a new kernel, we're going to be able to measure irritability and amazingness, and then we're going to try to predict the stockiness from that based on the machine learning off of these 50,000 compounds. Now, we're going to look at several different algorithms in the broad category of regression. So basically, this is a category where we're trying to predict most often properties of material based on other properties. So we're trying to learn relationships between the properties. We're going to start with linear regression, and linear regression is often lumped in with machine learning, but you can certainly think of it outside machine learning, and that's simply looking for linear relationships between properties. So we'll see that. We're going to discover that these properties are very complicated relationship between them. So linear regression won't work so well. So we're going to try several other types of methods for doing these regressions, and they really fall on algorithms that categorize. So they aren't. Some of these, especially the k-means or the k-nearest neighbor, really isn't specifically designed for this, but it works for this type of predicting relationships among properties. So 2 are related here: the decision tree, and basically this is an algorithm that just says yes or no to various decisions, and when it comes to regression, it's just comparing particular value of the function relationship between these properties. Now, that can work. It's very quick. It's relatively quick to learn, but it can be a little less precise. So related to this is something called the random forest algorithm, which is just a bunch of decision trees, and then they all these, just there's a prediction coming from each of these decision trees, and the random forest then sort of takes an averaging of that. Then different category is something called the state vector machine, and this is looking for planes, or if you're thinking about just 2D data, lines that would separate different clumps of data. And I don't actually know an awful lot about this algorithm other than that. I know that it can be useful for higher dimensional data, but it also takes quite a while to train. And we're going to be comparing some of the time it takes to train as well. And then k-nearest neighbor, this is a clustering, a primary clustering algorithm. So it's looking at what's common for a set of data points in the parameter space. And then if another data point has those characteristics, or several of those characteristics, then the prediction is made based on it being like those neighbors. And so that's another method that is sort of pushed into the regime of these generalized regression techniques. So trying to find a relationship between properties of materials. Okay, well, let's get to the lab and see how this all goes. All right, I'm gonna switch here now. Get this down. So we should have our chemistry introductory lab sequence, part 1. If you are just coming to this lab directly, I refer you to the first video in the playlist that goes over how we install the data sets that we're going to use, and introduces us to the course webpage, which is here. Everything we need to install is there. And again, I won't go over that because there's a video at the beginning of this playlist that does that. And we'll put a link into the description. Okay, so let's go back to our launcher here, and we will launch Cobber Machine Learning Synthesizer. So let's launch that. Let's see, it might take a while to launch, but maybe it didn't launch. There it is. Okay. Okay, so what we'll do is let's open a comma separated value. Well, actually, let's talk a bit about the lab first. So I kind of went over most everything here. We're going to be exploring Cobberland and looking at the 3 properties of irritability, amazingness, and stockiness. Looking for relationships between those. Linear regression, decision trees and random forests, support vector machine, and k-nearest neighbors. So if you're reading along in the manual, there's a little bit, very brief description of each of these, and some instructor highlights if you're an instructor. All right, we'll get to starting this, and this is obsolete. Hopefully, when you're looking at this, we have an updated lab procedure for this. We've already downloaded the launcher, and so we're using that to launch all of the programs we need for all 4 of the experiments in this mini course. So this is just talking about launching this one program. So we're starting right here with loading the data. So let's go ahead and load those data. So we're going to open a CSV, and then I'm going to go to our data set. And so we're looking for Cobber Machine Learning SYN, and we're going to look up the kernel data. So these data here are 50,000, are the 50,000 known kernels in Cobberland. And then these are some newly found kernels that we'll use at the end of our experiment to predict results. Okay, so let's open this up. And the first thing we see in the console is just the shape of the data. So there's 50,000, there's 4 columns. The compound number 1 through 50,000, and then irritability, amazingness, and stockiness. Okay, so the first thing we need to do is define the training split. And so a very typical one is 80-20, and that's the default of this program. So let's adjust this slider so that we're at 80-20, and it should be there right away when you opened it. Later in the lab, we'll look at changing this a little bit. Okay, So first, we'll select the algorithm and we'll start with just linear regression. And we will go ahead and run the training set. And we will see the actual versus predicted, the residuals. We will get a report on the mean absolute error and the mean squared error, along with the R squared, and also on the computation time, the time it takes to run the computation. So let's run this, and that's very fast, about 1/100th of a second, a little more than 1/100th of a second. Very poor, and we can see that both visually in the graphs, also very, very high errors, and although not as bad as one might think looking at the graph, but a bad R squared value. So clearly linear regression doesn't work very well. And so what is this saying to us? It's saying that there isn't a simple relationship between the amazingness, the irritability, and then the resulting stockiness. So this algorithm is not working very well. So let's go ahead and actually, yeah, what you should be doing then is recording these 4 bits of information. So create a table and pick up these, and you'll be able to then compare these across the different algorithms and see which is the best that we would decide to use. Okay, so let's try the different algorithms. Let's go ahead and do this decision tree. Keep the split the same, and then we'll run the training set. We see much better behavior, and so we're getting about 100 times longer, but in this case it didn't matter that much, still just 1/10 of a second, and a much lower errors here. So 133, well, 100 times lower error here almost, and then a much better R value. So that is with the decision tree. Let's try the random forest. Now we'll see that this will take longer because it's running a whole bunch of decision trees and it's taking the average. We should expect a slight increase, although this is quite good already, but a slight increase in this. So we'll compare the numbers. So let's run this experiment, and it's running now. So hopefully I don't have to pause the video, and okay, there, it didn't take too long. So 7 seconds it took. Better R squared value. We're kind of getting diminishing returns, but certainly better results here. You can even see more packed along this. So as expected, a random forest does better than a decision tree because a decision tree is just one member of that random forest. So it almost can't help but do better. Although we will be talking about this idea of overtraining, and that can be a problem. But usually we expect the random forest to do better than the decision tree. Okay, let's run the support vector machine. And I think I will pause the video here because this does, if I'm remembering right, this takes a fair bit of time. So I'll just hit the run. Okay, it's running now. It might take a little while, so I'm going to go ahead and pause the video and then come back when this shows up. Okay, so here we are. Took almost 30 seconds. So worse from a timing standpoint, definitely worse, at least at low values and around this jump discontinuity, although not bad up at high values of stockiness. So let's record these values, and so we actually do worse with the support vector machine. So this algorithm is not as well suited as decision trees for this particular type of data set. And this is what you're learning when you do the training set. And so that's why the supervised learning is important here, because we're able to characterize these differences from what they actually are. Okay, nearest neighbors, I think I probably will have to, I'll go ahead and run this. Oh no, I guess that was quick. Okay, so that was very fast, but did quite a good job, except right near the jump discontinuity, and that makes some sense because this is looking for clusters in parameter space, and there's a jump discontinuity here. So it's look what it's doing here. It's thinking this is over in this cluster and this is over in this cluster. So it's misassigning these points near this, misassigning these points to clusters near this jump discontinuity. So if this had no jump discontinuity, it would probably do a pretty good job. We see here, even with these outliers, still getting a pretty good R value, R squared value, pretty good mean squared and mean average value, absolute value. Okay, so those are our algorithms. So now let's go back to, so that was experiment 1. Hopefully we created a chart and you can kind of look at that closely and see what's good about each of these models. So let's start experiment 2. So let's take the decision tree model. So that was a fast one. So we'll go to decision tree. I'm going to rerun it here at 80. So I'm just going to run it at 80. And again, start making a table. And we will record some differences here. And let's see if we notice any difference. So we want to go to a 50-50. I guess this is all the way down. So 50-50. Not too much different. Notice very close. We're probably, and that's to be expected. You do see one real extreme outlier here, which didn't show up in the others, but numerically they're pretty similar. And then we have this outlier here. So this should just keep getting better. So again, not super easy to, not a dramatic difference here, but let's run the training. Still get that outlier here. Just ever so slightly better. So we're creeping down better and better. So let's try 70. Get rid of that outlier finally. So there's probably some real piece of data that's a major outlier that it's having trouble with, and now with enough of the training set being big enough, then it does a better job. So now we're getting to probably where we're going to start to be pretty much the same here. So a little bit of improvement, just way out here on this barely significant digit. So let's go ahead. We did 80, so let's do 90. Let's see if we get worse. We have too big of a training set. No, I actually did better. So it's harder with this small parameter space to show the concept of overfitting. So we're going to kind of push that to next lab. But what can happen is if you train too much on the data set, then it will get to know the noise of those data and not perform actually as well because it thinks some of that noise is real physical, meaningful stuff. So it's kind of a balancing act. And here it looks like we can train on a very large fraction of the data. Okay, let's go on to the next experiment. And we're gonna get some new information. And so I'm gonna set this back at 80-20 decision tree. I'm gonna rerun this. And now let's go, and unfortunately, for some reason, Microsoft Office is not working on my machine here right now. So I'm going to open up the new data set here in Notepad. And let's keep this here now. So you could choose some of these. In the lab I say choose 4. Let's choose this one and see. So we'll just choose the first one. So 375.1 so 375.119. So irritability, amazingness. So 3.75, 1.19. Let's predict the value. So it predicts 4.25. Let's see what it actually was for this new kernel. 4.68. Let's try one more. This is kind of extreme in all directions. So 951, 973. It predicted 100.22 or 0.23. So let's go look at what that was supposed to be, 100.34. So a very small percent error. So you can play around with some of these, see how well it does. You could try some of the other models. So if we did the random forest, it might do just a little bit better. Oh, let's go ahead and try that. So we'll do random forest, run. I think, remember right, this took about 8 seconds. Okay, there it is. So let's predict the stockiness. Oh, actually, I think it did worse, didn't it? Close. So 100.97 and 100.34. So a little bit worse, actually. Interesting for this particular one. And, you know, these are all just sort of randomly generated as well. So we do expect some noise in this. But we see that we're getting reasonable predictions from these learning models that we would not get from the linear regression model. All right, so with that, why don't you try to write a conclusion and kind of solidify in your own mind what's going on here. This is our first experience with real machine learning, albeit on artificial data, and we can see some of the effects of choosing the different algorithms and how those affect our ability to predict the relationship between properties. All right, so with that, I'll close and we'll see you next time.